Welcome to the next video, and I have a spreadsheet being prepared over here, but before discussion of this spreadsheet we will just come back to the Fluent, and you can see that the in the console over here we have certain information being presented after the generation of these particles. Okay, so the first information is with respect to the number of particles tracked, and that is mentioned as 66, and the number of particles escaped is 66. So what we can understand is this particular inlet what we have. Okay, this particular inlet has 66 faces, so this single surface is having 66 faces. Now the number of faces depends on the density of mesh. If your mesh is more denser, then obviously you'll be having more faces over here. Clear? So at each phase, or from the each phase, there is a droplet being injected into the domain. Okay, that is what is the number represents. Now after the droplet is being injected into the domain, the droplet will be interacting with the flow field, the continuous flow field what we have, that is the propane gas flow field, and it will try to escape from the outlet, and that is the reason we have escaped equal to 66. Now the reason 66 is mentioned because in some cases, I mean at this moment the case is very simple. In some cases the particles get stuck, okay, at some regions, and they don't escape. I mean all the particles are not escaped. Clear? So in that case you'll be having some lower number mentioned over here. For imagine as an example 50 particles have escaped, but 10 particles are stuck somewhere in the domain. So you'll be having a number of 50 particles written over here, or 50 droplets. So this will help us understand that there is some problem in the design which is making the particles stick to that particular locations. Clear? And now let us just come back to the spreadsheet. This spreadsheet is for your information. This is just additional information what I just thought to discuss. And the first thing is we have droplets, and the next thing is phases. 66 phases we have. So we have 66 trajectories, and each phase will inject each droplet. So we have 66 droplets into the domain. Okay, and if you remember, the diameter of each droplet is how much? I'll just open the injection, and the diameter is 1e minus 4. So I just wrote over here 1e minus 4. Now the radius is nothing but diameter by 2, so I got this value. Now each droplet is spherical in shape, so we can calculate the sphere diameter using the online calculator, and I got this value over here. Clear? And we know that the density of the material what we have created is 1000 kgs per meter cube. Clear? So I've written 1000 over here. The volume is known, the volume of each droplet is known, the density of each droplet is known. Therefore we can calculate the mass of each droplet. So I've just multiplied them, and I got the mass as 5.2 e power minus 10 kg. So this is the mass of each droplet which is into the domain at this moment. Clear? And if you want to calculate the mass of all the droplets, you simply have to multiply with 66. Clear? Because we have 66 droplets, just multiply with the mass of each diameter, I mean the mass of each droplet, I'm sorry, you will be getting the total mass. The total mass of all the 66 droplets combined at this particular location when they're entering is 3.4 or 10 power minus 8. Clear? And as we know that the mass flow rate was 1 kg per second that we have set up in the injection. Okay, so if you want to calculate the actual droplets per second, okay, what we have to do is we can simply divide 1 kg per second divided by the total mass. That will be the actual droplets per second, right? So this is a simple calculation which I just thought to tell you. So this the mass transported is that of all the droplets in that stream. Okay, and that is 2.9 e power 7 droplets per second, right? Now coming back to Fluent, let us just leave the calculations for a while, and for For a DPM simulation, for performing DPM analysis, there are two possibilities for us. I mean, we can couple the relation between the continuous flow and the dispersed flow in two fashions. Okay, the first coupling is called as one-way coupling. Okay, and the second one is called as two-way coupling. The kind of experiment what we have done right now is one-way coupling. And what do we generally mean with one-way coupling or two-way coupling? Okay, so one-way coupling in the sense, the momentum of the existing continuous flow what we have is affecting the dispersed phase. Okay, but the momentum of dispersed phase will not be affecting the continuous phase. That is what is the first one-way coupling option. Okay, so I'll just repeat it again. The momentum of this propane gas, which is the major continuous flow in the domain, the momentum of that particular flow will affect the momentum of dispersed flow, right? But the dispersed flow momentum will not affect the continuous flow momentum, right? So you'll be having some action of the existing flow on the dispersed phase. So the dispersed phase will react based on the calculated flow field, but the calculated particle trajectories will not react on the existing flow field, right? That is what is one-way coupling. And for this reason, the performing the job of one-way coupling is very simple. We just have to inject the properties and directly go to the post-processing and create the particle tracks, right? Now, what is two-way coupling? In the two-way coupling, what is happening is the both of them will be affecting each other. Okay, the continuous flow will be affecting the trajectories of particle or the particle trajectories, and the particle trajectories moment may affect the flow field. Clear? So it depends on your cases. At some places, if the continuous flow field is extremely large and you think that the presence of tiny particles may not impact that flow field, then one-way coupling is suitable. But if you feel that the existence of tiny particles, okay, may impact the flow field of the continuous flow, then you have to go with two-way coupling. Okay, in our case, the particle sizes are very small. You can see the mass of this particular, the total mass is such small value. Okay, it is 3.4 e minus 8. So we have just went with the one-way coupling. Now we must know the procedure for two-way coupling as well. Okay, so how do you do it? We just have to go to discrete phase and double click it and use this option, that is interaction with continuous phase. And we need to resolve the fluent simulation. And for while the fluent simulation is happening, I mean the simulation what we have performed for the propane gas will be restarted, and we have to wait until the convergence happen. And when that simulation is happening, in parallel with that, the DPM or the discrete phase model will be solving the particle trajectories. Okay, so based on the particle trajectory movement, the continuous flow will be affected, and based on this affected the continuous flow, the DPM will be affected. So both will be related to each other. So this will take a lot of time actually, and I'll just ignore as of now. Okay, but because we have many more things to discuss at this moment, so I'll just pause for this interaction of continuous phase, and we will discuss other significant important topics. And later when we are evaluating the soil erosion, we can just see the interaction of continuous phase actually. Okay, so I believe you have understood the difference between one-way coupling and two-way coupling, and also you must have enlightened with certain information about this total mass calculation of the droplets, and the number of phases which are involved, and the number of trajectories, the escaping and the tracking, all these things, because these are all the parameters that define the DPM models. Clear? So on this note, I'll just conclude the video over here, and in the next video we will discuss some other important or significant aspects in DPM that one must know for working with DPM models.